Right, so we have this problem here, 3 bars with thermal expansion and plastic deformation. The setup here is that we have these 3 bars. The top and the bottom ones are identical, material 1, an elastic, perfectly plastic material. And the middle one here is a standard elastic material. So here are the graphs. Bar 1, we load it. It has a certain Young's modulus which describes the slope of the linear section here, the elastic region. And then when we get to a certain yield strain, the stress in the material becomes a constant value y. And then material 2 is just an elastic material. The strain is a linear function of the stress, and we don't have a yield point. And in the question, we heat up our bars. Because they have a thermal expansion coefficient, alpha, so alpha 1 is just alpha, alpha 2 is twice that, 2 alpha. We heat them up, and because of their different expansion coefficients, in this case bar 2 is going to want to expand more than bar 1. And so we're going to have a stress, stresses in the 3 bars. And in the problem we want to determine what those stresses are. But a question that we had was, when we heat up our bars until the stress in bar 1 equals the yield stress, after it's begun to yield, how are the strains in bar 1 related to each other? Well, that's a good question. Let's have a look. In problems like these, there's one equation which always applies, and we should remember that. So, remember that the total strain in a material, this is the strain that we actually are able to measure, is broken into 3 portions. We have our elastic strain, we have our thermal strain, and we have our plastic strain. And we know from our constitutive relations that the elastic strain is given by our stress, sigma, over the Young's modulus E. We know that the thermal strain is given by alpha, our thermal expansion coefficient, times the change in temperature, and then our plastic deformation is just a number which is what we want you to calculate in the problem. So, we know that this always applies in every part of the problem, and that's something to remember. So even when the material is yielding, this still applies. When it's yielding, the plastic term is going to come into it, but the equation always applies. So that's one thing. There are 2 other things that you'll need for this problem. The first one is to remember that when you're doing compatibility relations, so when you're describing once there's some stress in the material, some thermal expansion, and you want to know what the length of the 3 bars are, you're going to be using your strain in order to write down your compatibility relations. So remember that it's always the total strain which enters our compatibility relations. So that's the first thing. The second thing to remember is that when you have a stress in your material, the stress is entirely described by your elastic strain. So the elastic strain is the only strain that enters into your stress formulas. So stress is entirely determined by epsilon E, our elastic term, which, as we have said, is equal to sigma over E. So, we have three things here. One, this equation relating our strains always applies, regardless of whether it's yielding or not. Two, the epsilon that enters into our compatibility relations the strain that enters into our compatibility relations is our total strain. And thirdly, that the stress is entirely determined by our elastic strain. Right, that should help you get started on the problem.